This video, we're talking estimating a population mean mu, which is a fancy average, but for a big, large group. And estimating, meaning, look, we can't talk to everybody, so how can we get a good guess where everyone's at, or at least where most people are at, just using some sample information. Now that just using, I don't want to spoil the ending here, but it isn't just with sample information. This Z statistic is going to rely on a little bit of population information to help us connect the sample to the population. So let's look at our examples here and we'll dive right in. So again, we're going to talk about a population mean mu, but we're not sure what it is. And so we get the next best thing, sample mean. And as we've talked in the past, ideally these are relatively close. And so we call that sample mean a point estimate, our best guess, or it should be close to the population mean. But how close? Well, that's where we get into a little bit of the statistics. And so let's look at this motivation, this example, and see how this thing is going to start off. So look, after a cruise boat docks, 36 rooms are randomly sampled and found that their average tip for a week of service is $44. That's just from the sample of 36 rooms. This boat cruise has 500 rooms. And so the question is, does this average tip of all 500 rooms mean this? Well, of course not, right? I can't just talk to 36 and somehow project that exactly. There's not a perfect relationship between these two, but it should be relatively close. So say an accounting computes a margin of error, a swing, if you will, of $2 with a 95% confidence interval. With 95% confidence, what is the average tip of all 500 rooms for this cruise boat's trip? Well, we have our best guess, our point estimate 44. I know what my swing is. I can subtract and add. I should be left with 42. If I subtract, that's the left endpoint or the smallest I can imagine the average being, or $46. That's the right endpoint or the largest we could imagine it being. And again, this confidence interval is for the actual population mean, that it's somewhere inside of here. It may be 42 on the low end, it may be 46 on the high end. And I'm making that claim, that prediction, with 95% confidence. There's a 95% chance that intervals built in this way will contain the population mean. What a powerful thing that I can talk only sample 36 and somehow get a pretty good range of values, a good understanding of how every room, if I added them all up, what that average would be. And that's exactly what we're going to discuss in this video. So there are actually two methods or two intervals for computing confidence intervals for a population mean. This first one is exactly what this video is, and then later we'll talk about a t-interval. So here we go. This z-interval, this is what I spoiled in the intro, is that it actually does need some population information. You need to have the population standard deviation. It has to be known. For instance, the population standard deviation is 9.1. Now I can use a z-interval. For a t-interval, it's something a little different. It's when I don't know the population standard deviation. It's if you're looking at the question and you have no idea what the population standard deviation is, okay, well, with that lack of information, then you need a t-interval. This Z and T interval distinction is different for some textbooks, and the one that we focus on, specifically OpenStax, relies on this distinction, and so we'll do the same in this video. Look, in order to perform a Z interval, we have to perform a check. We need to make sure our sample is big enough. This is exactly like we've talked about in the past for a sample mean normal distribution. We talked previously about, look, if you were finding, for instance, the probability that a sample mean is less than some value, if ever you're talking about how is a sample mean distributed, you had to make sure that our sample, the one that builds our sample mean, is statistically big enough. Well, how do we talk about that? Well, down over here, these two things have to be true in order to do a z-interval. The first one, classic, you have to know what the population standard deviation is. This should be in the question or in the example, in the phrasing, it should say, hey, the population standard deviation is 9.1, for instance. But the second thing, this is something to check, is that we need to have a large enough sample. In order to be normally distributed, my n has to be large enough. The central limit theorem tells us that, look, we really only need a sample of at least 30, 30 being fine, 31 being better. That's what we're looking for here. So this is our check. A very quick one indeed, just large enough sample, and then we can go into building those confidence intervals. Let me introduce the topic, or at least the argument for how these confidence intervals are usually constructed. And I'll do so by putting the steps or the processes on the left, and then right above me is the actual example where we can go through. So look, the first thing you need to do is you need to draw a sample size n, and with that sample, compute your best guess. For practically speaking, say maybe you're a student in a biology class and want to gauge the true average, the population mean for some exam, let's say exam 4 you took last week. You randomly ask 30 students for their score, and that's what this table is down below. And say maybe this is the unrealistic part, so you have to suspend your disbelief a little bit, that you know what the population, that standard deviation is. From these 30 students that you asked, you'll get an average, that's average in Excel, of 81.6. This is your point estimate, your best guess. So there's the first part. The second part is we need to calculate our standard error. If you'll remember, standard error is just a fancy way to say the standard deviation of the variable of your point estimate. Here's our formula over here. So to compute it, there it is. It should be 2.43, or the standard deviation that we knew from the beginning divided by the square root of n. And so that's the standard error. The next ingredient I'll need is a critical value. That critical value comes from our level of confidence. And so it really depends on how confident we want to be in our interval. The rule of thumb, anytime you hear level of confidence, the rule of thumb should always be 95% confidence. That's the rule of thumb that they usually just put out there, but certainly there are many and more in between. And so let's say you want a 95% confidence interval. Well, the critical value, 1.96, corresponds to this level of confidence. And I'll show where that comes from here in a minute. I then need to multiply that by my standard error, or my standard deviation for the sample means, and look at that, I get my 4.76. This is my swing. So I calculated my point estimate, my best guess. I now have my swing, my margin of error, which again is just a product of these two terms, my critical value and my standard error. But once I have this, now it's off to the races. We can generate that confidence interval. And if I can just move my head a little bit out of the way, here it is. We are 95% confident that the true average score, that is for everyone taking the exam, whether that was 100 people taking the exam or 2,000 people taking the exam, that the average for this exam is somewhere between, this is my point estimate, the mean, minus my margin of error. And it looks like the left, the smallest average I can imagine it being is 76.9. And the largest, if I add the margin of error, will get me 86.4 for the mean. And again, the beauty of these confidence intervals, because things are normally distributed, I know where roughly the center is. The center is roughly about, if I back up one, this 81.6, this average that I computed earlier. And because I know it's roughly around there, no matter if I'm talking about 2,000 students or 5,000 students, or even just 100 students, the shape should still remain the same bell-shaped curve. And the actual population size is irrelevant. All I need to compute is that standard error and this critical value, again, the critical value coming from the normal distribution and the standard error coming from the actual group, how spread apart my group is. And if I multiply this together, that'll be my swing, and I can make this prediction just based off of 30 students. And so these are the components of these confidence intervals. More practically speaking, how do we actually get that, for instance, the critical value that I mentioned earlier? This critical value actually has an origin story. It looks like this. This is a bit extra. This goes into the origin story as to where that Z value comes from, that Z alpha over 2, the critical value I was talking about before, based on beta level of confidence. And so if you like to just skip ahead to the next bookmark, you're more than welcome to do so. So if you remember, anytime you see a Z character in statistics, oftentimes it refers to the standard normal distribution. Standard normal just means you have a very particular kind of mean of 0 and a standard deviation of 1. And then we also have this Z transform that we talked about before, from going from a Z score to a regular piece of X data up top, a transform to go from one world to the other. This beta is oftentimes your level of confidence, where alpha is just the opposite relationship, 1 minus beta. And so when we talk about 95% confidence, that relates to beta equaling 0.95. This critical value, this alpha over 2, the one that we're really interested, comes from solving this equation. It says, look, what's the probability that a critical value, Z alpha over 2, this is like writing X for different distributions, that Z alpha over 2 is in between negative, whatever this value is, we're not sure, and positive, whatever this value is, such that it's equal to, let's say, 0.95, if we're trying to find the critical value that corresponds to a beta of 0.95. If you'd like to find this critical value, it's actually a nice way to do it using inverse normal, but I can show you a picture over here that this is what you're trying to solve. You're trying to find out what these two values are. This is your negative Z alpha over 2, and this is your positive Z alpha over 2. And so the real trick is just to use an inverse norm business, because you know what the mean is 0 and the standard deviation is 1. And so it's just a nice inverse norm problem. If you don't want to go through the hassle, though, I can move out of it just a minute. There you go. And you can see the table based on your level of confidence, the critical value associated with it. So look, if you wanted to figure out the 80% confidence level, you could. In fact, if we look at this table, let me slide out of the way a bit. Here it is, 80% confidence. The critical value is written there at 1.282. And that would adjust your margin of error. Notice it's smaller than our 95% confidence interval. And so it's not, my interval is going to not be quite as wide, which will give me a nicer, more narrow confidence interval, but I'm less confident in it, which ultimately makes it less worthwhile. So this is where that Z critical value comes from. Not that you necessarily need it though, because oftentimes this is something that Excel can do for you automatically. Let me show you. So here's how we actually build the confidence intervals using a Z interval in Excel. So we're going to need a couple ingredients. In fact, you should need 4 altogether. You're going to need a sample mean, or your point estimate. That's our best guess. You're going to also need the sample size. How many people did we talk to get that sample mean? You're going to need, and this is the special one, I'll star it over here. You'll need the population standard deviation sigma. And you'll also need, the last ingredient is your level of confidence. You will need these 4 ingredients to build a confidence interval for a population mean. If you have those 4, you're off to the races. One of the friendly things about a confidence interval is you really only need 2 things to actually put the confidence interval together, one of which you already have, and that's the sample mean. The second ingredient is this margin of error. There are 2 ways to compute it. There's the traditional, here we go, critical value times the standard deviation of the sample means. But the way that I would encourage you to use, I'll underline it right here, is the second method. And it says, look, if you type into Excel equals confidence.norm, you need 3 inputs. You need 1 minus beta, which for the fancy folk is just alpha. You need 2, your standard deviation. And then thirdly, your sample size. If you can type in those 3 ingredients, boom, you'll get your margin of error, no problem. And so with that sample mean that we started with, minus your margin of error, well, there's your left endpoint. And with your point estimate plus your margin of error, there's your right endpoint. And you can build these intervals, no problem. I get a reference. Here's a little formula sheet, very similar. You have the first method for computing the margin of error, highlighted over here, and the second one as well, where if you're going to use Excel, here's the function that you should be using, confidence.norm. Make sure if ever you're using confidence.norm, you have the population standard deviation, which again, the distinction, Z versus T, is different per textbook. Us, for using OpenStax, we're going to stick with their definition, and that is Z interval. You should know the population standard deviation. All right, that's enough with the semantics. Let's actually get into an example computing and working with these confidence intervals. First example, a researcher is studying the height of men with a certain medical condition. She draws a sample of 40 such men and finds that their mean height to be 68.5 inches. Assume that the standard deviation for the population of men with the condition is sigma equals 5. Class, if you want to know if people with this medical condition, maybe what's their average height? Can't talk to everyone with this condition, and so instead I'll just get a random sample of 40. First task, find a 90% confidence interval for the average height of men with this medical condition. Anytime you hear confidence interval, I'd encourage you, for us, we're talking about average height. That's a confidence interval for mu, and so I can know that my confidence interval is going to be of the form x bar minus my margin of error, x bar plus my margin of error, where this is my left endpoint and this is my right endpoint. So I can write out, to first start, left equals x bar minus my margin of error. Fortunately, one of the ingredients you get for free right there is 68.5. The margin of error, okay, that's what this is for. And you can open up Excel and try this on your own. I'd encourage you to see if we get similar numbers, but I'll write it just like you would type it. You would type in first equals confidence dot norm, because we're using a Z interval. We actually know what the population information is. I'll write it over here. Z interval. And then I have 3 inputs to put in here. The first one is just 1 minus beta. How confident are we in interval? They want a 90% confidence interval, so let's just type in 1 minus 0.9. Or if you want to be a little bit fancy with it, you can type in 0, 0.1, or 0.1. The next ingredient that I need is the standard deviation. It's a nice number like 5. And the last number I need is n, my sample size, which should be 40, how many people I talked to. And then just like that, I should quickly get a margin of error, 1.3. So now we have the two ingredients. I have my point estimate and my margin of error. Let's add and subtract these numbers together. I should get 68.3 minus my margin of error of 1.3. And then it's going to be 67 for my left endpoint. For the right endpoint, again, I need to add the margin of error, x bar plus our margin of error. That's 68.3 plus 1.3. That sum should be 69.6. So this is my range of values, again, for the average height of men with this condition, 67 inches all the way to 69.6 inches. And that's the answer we're looking for. And so what can we do, or how can we apply this particular example? Let's say a 90% confidence interval isn't enough. Somebody computed a 99% confidence interval, yields a margin of error of 2. And the interval between, for the population mean of people with this medical condition, is somewhere between 66.5 and 70.5. From census data, it's actually known that the average height of men in the general population is 70 inches or 5'10". Is it reasonable to assume with 99% confidence that men with this medical condition are shorter on average than men in the general population? The way I encourage you to set this up is let's accurately compare the two. Look, the mean from the people in the medical condition is somewhere inside of this interval. I'm not quite sure. 66.5 to 70.5 versus in the general population, so I'll write mu gen. I know exactly what it is. There's no ambiguity about it. I know it's 70 inches. And so the big question is, can I say with 99% confidence that this group here, medical condition, are shorter? The short answer is no, and here's why. Notice this 70 is in here. In fact, it's possible the mean height for people with the medical condition is equal to 70.5. In fact, people with this medical condition may even on average be taller than the general population. And so unfortunately, no, I cannot make that claim that people with this medical condition are shorter. And again, the big deal is that people with this medical condition could have a mean height anywhere in this interval. I mean, they could be shorter, could be 66.5, but I certainly can't say with any kind of certainty that they're always going to be shorter. So what can I do to maybe adjust or fix this so that I can get a proper result? And there's actually one ingredient that if I could change, go back to the drawing board, then maybe I could get an appropriate answer. This is the motivation as to why we look at sample size. And so if you'd like to go down and skip to the next bookmark, you're more than welcome to, but I want to explain the reasoning behind it. Look, that 99% confidence interval that was computed earlier really had too wide of an interval. It contained 70. If there was some way that I could shrink my interval down, well, then I could make that inference that people with this medical condition are shorter on average, because if I had a more narrow interval, I wouldn't capture 70.5. There's a couple different things you could do. You could say, well, hey, why don't I just gather a different sample? And then fingers crossed, you get a value you like. The problem with that, the margin of error will stay the exact same no matter what sample you pick, because the margin of error is only based on the normal distribution, how confident you want to be, and also how wild your group is, which if we're using population standard deviation isn't going to change. And so the only thing you can change is the sample mean, but the problem with the sample mean is it's random, right? One day you might sample and get 68.5 like we did earlier for my sample mean, and the next day you might get 68. But even if you get a smaller mean, that margin of error, that swing, still gives you an unhelpful confidence interval. So we can't just rely on chance to maybe hopefully get a smaller sample mean. Instead, we need to think about getting a better sample mean. And here's the idea, is that the larger sample size we gather, the better our point estimate's going to be in predicting the population mean. And so if we truly do believe that the population mean is less, then the larger my sample is, the better my guess is, the more narrow my confidence interval is. And there's actually a very fancy way that we can choose our sample size to fit the condition we need. How do we choose our sample size? We actually look at this formula for the margin of error, and we solve for n equals. You don't have to do that task, but if you do, you'll end up with the formula on the next slide. This is how you choose sample size for confidence intervals, particularly for a population mean. You need a couple ingredients in order to do this. Those are highlighted in this phrasing up here. We can look, if you're looking for a smallish such sample sizes, which guarantees a certain margin of error, E, you can use this formula over here. We have really 3 ingredients to pick from. The first one is a critical value, Z alpha over 2. And then again, that Z alpha over 2 comes from, I'll highlight it over here, this table, where we have different critical values depending on your level of confidence. And so again, if I have a level of confidence of 0.95, I can pick, there it is, my critical value of 1.96. I also have a margin of error, again, depending on what the desired margin of error is. And then I also have a population standard deviation as well. If you work these ingredients appropriately, multiply, divide, and then afterwards square, you'll end up with the appropriate sample size. As one little side note, whenever you're computing the margin of error, make sure you always round up. There's actually a really good reason as to why the numbers work that way. You always want to round up. Again, no matter if you get 0.1 or 0.7, you should always round that number up to the nearest person or whatever your sample is. Here's an example of us picking sample size that'll fit a criteria. If you remember the example we did before, we looked at a 99% confidence interval and got a margin of error of 2. But that margin of error was a result of, yes, our population standard deviation, but also in our sample size. And so if I can maybe talk to more people, maybe I can get a more appropriate margin of error. And so that same phrasing we had before, but I want to conduct a 99% confidence interval, but instead of it being 2 margin of error, I want the margin of error to be 1.3 at most. Assuming that the population standard deviation is 5, as it was in the previous example, what is the minimum sample size required for this estimate? I would encourage you, anytime we're asking for sample size, we know what that's looking for. It's looking for n equals, we can write out the formula. The formula looks like this: Z alpha over 2, standard deviation divided by that margin of error, and the whole quantity is being squared. We have a couple ingredients to pick from. I'll first start off with this critical level, this Z alpha over 2 business. Again, they're telling us that our level of confidence that we're picking is 0.99. You can refer to the table in the previous slide. In fact, I'll show it real quick. That from that table, if I'm looking at a 99% confidence, that critical value down below is 2.576. And so that's going to be the critical value that we're going to record here. Critical value Z alpha over 2 is equal to 2.576. And so that's our first ingredient, 2.576. And then I have the population standard deviation. Again, it's given right up top is 5. The margin of error that we're hoping for, it was 2, like we got before, but we don't want to do that. Instead, I want a margin of error of 1.3 and then square it. If you multiply, then divide, then square, we should end up with a number of 98.16. You might be tempted to round down, but for these sample sizes, you always want to round up. So this should look like 99. In this case, this is people with a medical condition. 99 individuals is how big my sample should have been. So again, I talked to 40, I got a margin of error of 2. If I talk to 99, I'll have a margin of error of 1.3. Here's a little side note to show. I'll get out of the way. I typed it up in Excel for you for reference. But if you change just that one ingredient, here it is that third input, to 99 for your sample size, that's confidence.norm, 1 minus beta, population standard deviation 5, and there's your sample size 99, you will end up with that margin of error. And if we use that same sample mean that we calculated earlier, 68.5, look at that, I'll get an interval from 67.2 all the way to 69.8. And so now we can make that claim like we wanted to. If you remember, the mean in general population height was 70 inches. And so now that 70 is outside of my confidence interval, I can make that claim that people with this condition on average are going to be shorter than the general population. Again, on average, doesn't mean it's a guaranteed for everybody. As an important side note that I want to make, just to clarify, look, this 68.5 was based off of our sample of 40 individuals. But as we know, This sample mean is a random variable. It's completely random, right? It depends on who you talk to, what data you're averaging out. So if I do talk to a fresh 90 people, well, who knows? I might get a smaller number. I could get a sample mean of 67. I could get a sample mean of 69. Right? The sample mean could be random. And so it's not guaranteed that you'll end up with a nice interval, but for the most part, we can assume that the sample mean should be relatively close, meaning that my interval will certainly be less narrow, and hopefully if that sample mean is small enough, it'll drag its way down. And certainly this interval that I've conducted has a 99% confidence interval, meaning intervals conducted in this way are very likely to contain the population mean. Not guaranteed, right? We could be completely off base, but hopefully it's relatively likely. Example 3. A fast food restaurant executive wishes to know how many fast food meals teenagers eat each week. They want to construct a 95% confidence interval with a total error of 1, with a margin of error of 0.5. So again, total error, when I'm looking at this confidence interval is 1. So when you look at each half, of course, 0.5. A consultant has informed them that a previous study has found a mean to be 4.9 meals per week, again, on average, and a standard deviation to be 3. What is the minimum sample size required to create the specified confidence interval? They want a confidence interval that is pretty narrow, margin of error of 0.5. And from the past, they know what an average was. Maybe it was from all the way back from 1990. It's way back in the day. And so we want to get a good estimate, a good idea. So in order to build that confidence interval, I first should commission how many people do I need to talk to? And so let's do it. If we're looking at, hey, what should the sample size be? We have a formula for that. It looks like this. N is equal to Z alpha over 2 times my population standard deviation divided by my margin of error, all squared. So let's identify each ingredient, then we can multiply, divide, and square, and we can get the sample size we need. For the first ingredient, I'm looking for this critical value. This critical value comes from beta, your level of confidence. Again, it comes from that table, if you will. So if I'm looking at 0.95, we write like this. If you look at the table, it'll tell you real quickly that the critical value we're interested in is equal to 1.96. I mentioned this earlier, so I'll try to be brief. But 95% confidence is the most common confidence that we want. In fact, for any published study, that tends to be the rule of thumb that people use. And so to that end, 1.96 is a very common critical value. 1.96 times my population standard deviation. Again, don't be fooled by this 4.9 business. 3 is our population standard deviation. And the margin of error is 0.5. Again, with a total error, my interval width being 1. So we get that 0.5. Here we go. If you multiply, divide, and then square correctly, we should all end up with 138.29. And that should be our sample size. So if you're tempted to box that, please don't do that. Instead, we need to round up every time. And so I'll have 139. In this case, this would be 139 teenagers that I need to talk to in order to get a good idea about their average fast food meals each week. 139, and I'll generate the proper confidence interval. So if I move out of the way here, I did the work in Excel just to kind of demonstrate what that would look like. If I did get a point estimate in X bar of the same what it was in the past, okay, so that's a little bit of suspend your disbelief, and I did confidence.norm with 1 minus beta, a level of confidence, my standard deviation of 3, and my N, sample size of 139 people, I will get the appropriate margin of error, 0.5. Math works out. And so then if I add and subtract that to my X bar, I'll end up with this confidence interval from 4.4 to 5.4, which, look at that, has a total error of 1, just like we wanted. And so that way we can kind of control how wide our confidence interval is going to be. Again, the only qualm that we really have is this relies on knowing a critical fact, and that is this population standard deviation. If you don't have that ingredient, there are ways that you can take a best guess where this population standard deviation is reliable enough to use in building our confidence interval, which certainly isn't always the case. All right, I got one more example for you. To estimate the number of calls to expect at a new mental health hotline, volunteers contract a random sample of 49 similar hotlines across the nation and find the sample mean is 352 calls per month. Assume that the population standard deviation is known to be 30 calls per month. we'll round our answers just to the nearest whole number. So if we're going to build a new hotline, we'd like to hire some individuals, but we need to know how many people to hire, which means we need to know demand. How demanding is this place probably going to be? And so we talk to other places, 49 different ones, and we find this is a good average. What we want to do is construct a 95% confidence interval for the actual mean number of calls. Population mean equals question mark. Again, this mean was just conducted by those 49 hotlines. That's their average, not, let's say, the nation's, or if we're specifically talking about a county or what have you. Anytime you hear confidence intervals, I'd encourage you to write out what we're interested in. We're interested in the mean, so that should be X bar minus my margin of error and X bar plus my margin of error. That's my left endpoint and my right endpoint. That's how we can always start these intervals. And so if I'm looking at my left confidence interval, that's X bar minus my margin of error. Well, we know what X bar is. That was this 352 calls. For the margin of error, that's where we'll need a little bit of Excel. And I'll start it like this. Equals, we should write confidence dot norm. You might be asking yourself, why are we doing dot norm? Well, I know what the population standard deviation is. It says it's up top at 30 calls per month. And so that's going to dictate, I know I'm doing a Z interval, which Z intervals are dot norm or normal distribution. I should be typing in 3 inputs. The first one is 1 minus beta, our level of confidence. They set it in this part A here. We want to build a 95% confidence interval. So I can type in 1 minus 0.95. Or if you want to be fancy, you can type in 0.05. The second ingredient I need is the standard deviation. That's 30, as I talked about earlier. And the last ingredient is just N, how many people did I talk to? Or in this case, how many hotlines did I investigate? 49. It's my sample size. N. And so I'll end up with a margin of error. And again, you can check me, go in Excel, type in just like I wrote. You should end up with approximately 8.4. You might get more decimals. So I have the 2 ingredients I need now. The sample mean X bar is 352 minus my margin of error, which is 8.4. You can subtract these together. You should end up with 343.6 for my left endpoint. On the right side, that's X bar plus my margin of error. That's 352 plus that 8.4. And I'll end up with 360.4. And these are the 2 endpoints that we need to complete our interval. 343.6, 360.4. And so look, I don't know what the actual average is, but I can tell you, just for my anecdotal, the 49 individuals, that it's somewhere between 343 calls and 360 calls with some change. And so what can we do with that interval? Part B. Understaffing a call center can lead to long hold times, which provides poor service, of course. But more importantly, is dangerous in this field, the field of mental health hotline. So on average, how many calls per month should the hotline prepare for at most? Like, what's the worst case scenario? Well, the highest average I could imagine it being is mu is equal to 360.4 calls per month. I'll write it like this. Calls per month, we'll abbreviate MO. That's the largest average I could imagine it being. But one thing that's important to note is, look, that's an average per month. Averages is me taking the highs and the lows and me putting them all together. So this high average is even a little misleading because, again, it takes into account those random days where we got 700 phone calls and those smaller days where I only got 2. But I need to be prepared for the 700 phone calls in a particular month. And so how do we compensate for that? Let me show you. Notice that if we look at this average in a daily sense, that would mean I divide it by 30 days in a month. And so I'd end up with 360.4, the highest average divided by 30, leaves me with 12, roughly, calls per day. And a standard deviation of 30 divided by 30 days equals 1. So now I'm looking at daily numbers instead of monthly. By the empirical rule, that was that plus or minus 1 standard deviation, plus or minus 2 standard deviations, and here we go. The mean plus or minus 3 standard deviations will capture 99.7% of my data. So moving in both those directions. So the question is, for how many daily calls should the center prepare for on the low end and on the high end? And that'll capture most, 99.7% of days. Well, we can compute this average, and keep in mind, for these, we're looking about how daily calls. And so we're looking at this 12 average and the standard deviation 1. So we have plus or minus, we got to do them both. So I'll look at the smaller one first. That should be the mean, 12, minus 3 times the standard deviation, which is 1. So this is just 12 minus 3 is 9 calls per day. And on the high end, the right side, that'd be 12 plus 3 times 1, or 15. So it looks like, again, we're not necessarily concerned about the average, especially as a call center. I want to make sure that when we get a high volume of calls, that I'm going to be prepared for that high volume. So really on a daily basis, the call center should prepare roughly between 9 on the low end calls per day, but 15 would be the best. And that's kind of like, you can think about it like your ceiling and your floor for how many calls you can expect to happen in a day. But again, we get that from taking an average, putting it per day, and then using the empirical rule, because these things are normally distributed. We know how the mean behaves, and then we can build out that prediction. So let me clean up and wrap with this. Our confidence intervals are best guesses. When we look at these range of values, this 343 to 600 to 360, that's for a population mean. These always come from the smallest little sample that we gathered, in this case 49. One thing that you'll notice is these confidence intervals, it doesn't matter how big your population is. As long as you know the shape is bell-shaped, and you know what the spread is, in this case the spread was, standard deviation was 30, well, I can use those ingredients in order to build out a proper confidence intervals. Whether that confidence interval is for a population of 1 million, 10 million, the shape is all we're concerned about. And that's what these confidence intervals build. Just like I said in the beginning though, these confidence intervals rely on something that's oftentimes not known, and that's this. Oftentimes I don't know how my population is shaped. And so to that end, oftentimes intervals built in this way may be a little off. And so we'll see in the future maybe better ways to build an interval that doesn't rely heavily on population information. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.